Section 10.3, Lagrange error bound. And we start with Taylor's inequality. Suppose that P sub n of x is the nth degree polynomial approximation for the function of f about x equals c, and m is the maximum value of the derivative of the next derivative on the interval c to b, or b to c if b is less than c. Then the error in using the polynomial value P sub n of b to estimate f of b is bounded by the maximum value of the derivative over n plus 1 factorial times b minus c to the n plus 1. And really what they're saying is that the maximum value is going to be less than the value of the next term. That is, the remainder r sub n in Taylor's formula satisfies the inequality. The remainder, or the error in our approximation, is less than or equal to the next term. Find the fourth degree Taylor polynomial for f of x equals e to the x centered at x equals 1. So all the derivatives of e to the x are e to the x, and if we plug in 1, we get e to the 1, which is just e. So all the coefficients are e, and then we just build the Taylor polynomial. Estimate P sub 4 of 1.2. So we plug 1.2 in for all of these x's, and we get 3.320109425. I'll spare you the agony of watching me plug this into the calculator. Find f of 1.2. Well, that would be pretty quick. We would just go e to the 1.2. And let's call that the actual answer. So 3.320116923. Now, if you subtract these two, you get 0.000000749 and so on. So this is the error. This is the approximation. Let's call this the actual answer. And by subtracting, we get the error of those two. What is the sixth term? Well, here we have 1, 2, 3, 4, 5. They have 5 terms here. So the sixth term would be e over 5 factorial times x minus 1 to the 5th. And that'd be the term after this one right here. Evaluate the maximum error for the fourth degree Taylor polynomial, and we'll discuss using 3 as the maximum for e. Well, this right here is the next derivative, but we know that this derivative is not going to be more than 3. So we're going to round this up to 3. Now, if we evaluate the maximum error for the fourth degree, it's going to be, the error is going to be less than the next term. So the value of the next term ends up being 0.00008. And that's not using e, we used value 3 to get that answer. That's why it came out as rational and not irrational like e would. Give an interval that must contain f of 0.2. Well, if I have no idea how much money you have in your pocket, but I'm going to say a really good estimate is $10. And I think that I could be $2 off. Well, that means if I take 10 plus 2, then you have at least $12. And if I take 10 minus 2, then I know that you have at very least $8. So I'm guessing if this is a really good estimate, then, and I know that the error is not more than 2, then you have either $8 to $12 in your pocket. That's kind of what we're doing over here. We're going to take the estimate. Here's the approximation. And we're going to add on what the maximum error could possibly be. And that's this number right here. Then we take the approximation and subtract on the biggest error we could possibly have. And that's this number down here. Now what we're saying is the exact answer is somewhere in between here. Here's the actual answer. And that number fits in between these two numbers right here. Let f be a function that has derivatives of all orders on the interval -1 to 1. Assume f of 0 is 3, the first derivative is 1/3, second's -1/9, third is 4/27, and the fourth derivative has a maximum value of 7. Find the third degree Taylor polynomial about x equals 0 for the function f. And here is the Maclaurin polynomial, since we're centering this at 0, using those coefficients. So 3 using those derivatives. There's the -1/9, and here's the 4/27. Use your answer to part A to estimate the value of f of 0.4. So we plug this into the calculator, and this is an approximation of the function value. Now, we don't know what the function is, so we're not going to be able to find out what the actual value is. What is the maximum possible error for the approximation made in part B? Well, all we're really going to do is we're going to get the next term. So that's going to be 7x to the fourth over 4 factorial. So we know that the remainder or the error of the third degree is going to be less than the value of the next term. So there's 7x to the fourth over 4 factorial with 0.4 plugged in. So this has to be the maximum error because we use the maximum value for the derivative. Give the interval that must contain f of 0.4. So the exact answer must be between these two numbers because we're going to take the approximation. Here's what I think you have in your pocket. Here's the error that I could possibly have. So we're going to add those two together and get the highest value the function can be and subtract them, and this is the lowest the exact value can be because we're saying this is the exact value. It has to be between those two right there. Let f be the function given by f of x is sine of 2x plus pi over 4, and let p of x be the fourth degree Taylor polynomial for f about x equals 0. So let's find the Maclaurin polynomial for this function by plugging in 0. Sine of pi over 4 is square root of 2 over 2. Then the derivative of sine is cosine, but we're going to multiply by 2. So there's the chain rule. And that's going to, cosine of pi over 4 is going to be square root of 2 over 2, but this 2 is going to take away, cancel with that 2. So cosine, derivative of cosine is negative sine, multiplied by 2, we get 4. Sine of pi over 4 is again square root of 2 over 2. But when we multiply by 4, we get negative 2 square root of 2, and so on. So derivative of negative sine is negative cosine times 2. Derivative negative cosine is sine, and then times 2, and you get the 16 there. So there's the derivatives right here. And we build the Taylor polynomial, or in this case, the Maclaurin polynomial. Use the Lagrange error bound to show that the exact minus the approximation is less than 1 over 3,000. So the error, in other words, this is error, is less than 1 over 3,000. Well, let's take the next derivative. We need the next term. We need to find out what would we put here for the next term. Well, if we take the derivative of this up here, the derivative of sine is cosine, and then times 2, 16 times 2 is 32, and we would get the value of this function right here, which is square root of 2 over 2. Now, if we take the square root of 2, and we divide it by 2, we can see that that is actually less than 1. But the maximum value of cosine is equal to 1. So we don't actually use square root of 2 over 2 to approximate the error because we might have error that's actually more than that. But if we make this a bigger value, if we make this 32 times 1, then we're guaranteed that the actual answer is in between the two values we're going to get, and we can actually say that the error is going to be less than what we calculate. So now the error on the fourth degree Taylor polynomial here is just the next term, but we're going to alter it a little bit. Instead of using square root of 2 over 2, we're going to use 1. So that becomes 32 x to the fifth over 5 factorial. That's the next term, and that's exactly what's here. But now we've plugged in 1/4 for the x. And then we do a little math. So 32, 1/4 to the fifth is 1 over 1,024. That actually cancels out to 1 over 32. And then we can just multiply the top and bottom by 32. Those cancel. And the error is less than or equal to 1 over 3,840, which is less than or equal to 1 over, well, it's actually less than 1 over 3,000. The trick on this one is sitting right here, knowing that instead of using that value, we actually have to use 1, because that's the maximum value for cosine. Alternating series remainder. Suppose an alternating series satisfies the condition of the alternating series test. In other words, they're saying is if the alternating series converges. Namely, that the limit as n approaches infinity of a sub n equals 0, and a sub n is a decreasing sequence. If the series has a sum s, then the remainder, or the error is equal to s minus s sub n is less than a sub n plus 1, where s sub n is the nth partial sum of the series. Now that's the next term. That's the term left off, the n plus 1 term. In other words, if an alternating series satisfies the condition of the alternating series test, you can approximate the sum of the series by using the nth partial sum S sub n, and your error will have an absolute value no greater than the first term left off. So it's very similar to the Lagrange error bound. Let P sub n of 1/2 represent the nth degree Taylor polynomial for g about x equals 0, evaluated x equals 1/2. So we've plugged 1/2 in, where g is the function f. Use the alternating series error bound to show that the approximation minus the actual, which is the error, is less than 1/500. So we're going to use the fourth degree right here. So we're going to use 1, 2, 3 terms. Here's your fourth degree. Now that's the approximation. And the error is going to be less than the value of the left off term, the next term. So here's the approximation. Error is less than the value of this term. So r sub 4, the remainder, or the error, is less than or equal to, we're going to grab this one right here, plug in 1/2, because that's where we're evaluating this at 1/2. 1/2 to the 5th over 20, that's 1/32. We can multiply the top and bottom by 32 here, and that's 1/640, which is less than 1/500, which is what we were supposed to show. Number 6 from 2018 test, the Maclaurin series for natural log of 1 plus x is given by this function right here. On its interval of convergence, this series converges to natural log of 1 plus x. Let f be the function defined by f of x equals x natural log of 1 plus x to the third. So let's start out with plugging in x over 3 in for all of these x's. So we're going to do a replacement first. We're replacing x with x over 3. So we have x over 3, x squared over 3 squared, x to the third over 3 to the third, x to the fourth over 3 to the fourth. And that's right here. Then we're going to multiply all of that by x. So x squared, x to the third, x to the fourth, x to the fifth. And we end up with this function right here. And we got the general term for them as well. There's the general terms. Determine the interval of convergence of the Maclaurin series for f and show the work that leads to your answer. We have the limit as n approaches infinity of x to the n plus 2 over 3 to the n plus 1 times n plus 1. And then we'll multiply by the reciprocal. We have one extra x, one extra, and we have one extra 3 in the denominator. Now the natural log of n, or the limit as n approaches infinity of n over n plus 1 is 1. So we have absolute value of x plus 3 is less than 1. Split the absolute value, and our interval of convergence is -3 to 3. Now for the AP test, and we're not quite ready for this yet because we haven't done all of the tests, we're going to plug in, we should plug in the endpoints. So here's plugging in -3, and when you plug in -3, you get 3 to the n plus 1 over 3 to the n times 1. Now that's 3 over n, and this diverges by harmonic series. So the interval of convergence does not include -3, but now when you plug 3 in, you get -1 to the n plus 1 times 3 to the n plus 1 over 3 to the n times n. So those cancel right here, and we have one extra 3. But this, if I pull the 3 out front, this is the alternating harmonic series, and this converges. And so the interval of convergence is actually -3 to 3. Now we're going to test endpoints later. Let P sub 4 of x be the fourth degree Taylor polynomial for f about x equals 0. Use the alternating series error bound to find an upper bound for P sub 4, in other words, the approximation, minus the exact. In other words, for the error. And it's a fourth degree. So if we go back to this polynomial, here's the fourth degree right here. So we're actually going to use this one right here. We're going to use the absolute value of that. So the error of an alternating series is less than the first omitted term. So here's that first omitted term with 2 plugged in. So 2 to the 32, let's see, 2 to the 5th, is 32, but we can take away 2 of those. So there's taking away 2 of those. That's 2 to the 3rd over 3 to the 4th. That's 8 over 81. So the error is less than or equal to 8 over 81 for that alternating series.